Okay, so we shall get started. When it comes to introducing our speaker today, I have already managed to fail before I say a word, in that I misspelt your name on both the website and the posters advertising this talk. So I'm reluctant to do too much introduction, but thankfully the speaker today is going to be doing most of their own introduction for me. Our speaker, Kevin Zack, is going to be introducing connections between his undergraduate studies here at Sonoma State through graduate school and then looking into the future. So thankfully he's going to provide us with a wonderful summary of how he was, how he is, and hopefully how he will be. So with that said, let's welcome Kevin Zack.
Thank you. Thank you. Welcome. This is my second What Physicists Do. My first one was 4 years ago when we launched T-Logo-Cube, so it's interesting being back here with the experiences that I've had. And a little bit different dynamic because I don't know any of you except for the professors. So before I was talking to my peers and now I'm talking to strangers, so that's kind of fun. Basically what I want to do is kind of show the connections between the students that are taking the physics classes and then how that actually helped me in grad school. Because I know when I decided to go to grad school, I had no idea what it was going to look like at all. And so this is one particular path that you can take. There's a lot of them because I ended up, going to electrical engineering at the end there. And there's, you could talk to Hunter Mills around. He has a slightly different path going to Stanford. So I started January 2012 to May 2014 here at Sonoma State. I transferred from Santa Rosa Junior College where I went back to school after being a journeyman electrician. And my claim to fame, and I try to stick it in every talk I possibly can, is when I was an electrician I worked at Metallica Studios. So if you know their Death Magnetic album, I wired the soundboard for that. And so there's my contribution to society. And then trying to do a little bit better from now on. So I got my BS in physics and I have a concentration in applied physics. So most of the things that you're going to see are more hands-on and less theoretical because of the applied physics. I also have a minor in electrical engineering from Sonoma State here. And most of my research was done at NASA EPO, which is now SSU EPO, and three main projects that I worked on, which was S4, small satellites for secondary students, the HVLPS, high voltage, low power supply, and T-Logo-Cube, which depending on how much advertising it's still going on, most people probably know a little bit about that. So S4 was a really fun project. It was kind of the introduction to this style of life with engineering for me. So small satellites for secondary students were basically making payloads for sounding rockets and balloons. And this was the first time that I went from doing a hobby level kind of engineering, if you want to call it, to something that was actually needing to be debugged fully, and because it was going out to teachers across California. And so we had real-time telemetry with Wi-Fi. And so what this forced me to do, and if anybody has ever worked with Lynn Kaminsky, you'll know that if you say, oh, I can program something in C, she'll go, good, do it in Python. And so I had to learn, you didn't do that? Well, it wasn't Logo. Logo was new when I started. So through that, I knew a little bit of C programming from playing with Arduinos. And so I wrote the code for the payload here in C. And then I had to do the Java side things in Java, so I learned Java, which helped me tremendously throughout my career, both here and in grad school, because I ended up writing GUIs for test plans and everything constantly, and evolving programs that I wrote here to something that I could use. And the fun part was I became a level 2 Rocketeer through that program. The right-hand side rocket, you can see that was my level 2 launch certification, and I built both of these rockets, which was a lot of fun. So kind of hands-on. And so the payload, again, was kind of like an Arduino. You have a SD data logger and some sensors and everything. And so this was the beginning. This was the beginning of everything. So I kind of wanted to show this in the form so that as you see the things I've done at grad school, how things kind of shrunk down and they became a little bit less modularized and more specific. The next thing I worked on for Dr. Garrett Jernigan was a high voltage, low power supply for a CGT array, which is a cadmium zinc telluride array looking at hard X-rays and gamma rays. And this was kind of my first introduction to feedback loops. And so I was using an MSP 430 to control the voltage to minus 600 volts, so plus minus 1 volt range was kind of the target that Garrett wanted. And so we had a high voltage power supply, this little M-code we called the sugar cube of death because it was a little centimeter by centimeter, and started all of this in a garage, my friend's garage, when we were building it, had a box, and when we first fired it up we actually put his motorcycle helmets on because we were like, if it's going to blow up, at least we have something. So transitioned a little bit from that. And this was the first introduction to micrologo. And so using micrologo as the language for the feedback loops. And then from there, Professor Bob Twiggs came and visited Sonoma State University, and he was one of the co-founders of the CubeSat idea. He was the Stanford one, if you know anything about the history of the CubeSat. And he saw what we were doing here, and at least from my perspective, this is the way it happened. He saw that we were doing here with S4 and all of this and said, you know, hey, I have a launch slot in 3 months. It turned out to be a little bit longer than that, but 3 months. And if you can build a Pocket Cube, we'll launch it for you. And so not knowing what that entailed, we were just like, sure, let's do it. And so we were able to develop T-Logo Cube. And basically the main goals of this was to launch and fly micrologo on orbit, to do some basic downlinking of telemetry, uplink a command and have it respond, so kind of like a hello, if you can, so we can actually talk to it. And the magnetometer, we took data from it and got the spin and precession rate using Fourier transforms. Now this is important because I reused that, you'll see a little later, in my graduate career, that idea. And so hopefully through this kind of SSU thing, as I go forward, you'll see, oh, I remember you doing something like that before, and so building on what you've done before. So and the secondary goals were torque coils and radio configuration changes and stuff. And it was launched November 21st, 2013. It operated for about 8 weeks. I think we did most of our primary goals. I think we did all of our primary goals and some of our secondary goals. It's what actually launched me into my graduate career, because I gave a talk at Cal Poly. It's actually some of the pictures from it, and met my advisor, Dr. Dave Klumpar, there, and he said, why don't you come on up to Montana State University? And so it was one of the places I applied to. So again, kind of developed the flight software in micrologo, and I just kind of wanted to show the picture of the development lab. So this is Darwin 305E, and so it was a room that's not that much bigger than this, and we had 3 of the team people working in there constantly in cramped quarters and kind of developing this lab. It was the nuclear prep lab, and it was kind of the first time that I was actually doing research in a research environment where there was actually tools available, and it wasn't in my garage, which was kind of nice because it was warmer. And then probably the most exciting thing in my life happened so far, which was when we actually heard T-Logo Cube. The first packets up there, you can see the little blips in the field of blue. That's the power, basically, of the peaks, and you can see that we sent a command and it responded to us. So this is at 650 kilometers up. So if it was 1 degree on the horizon, it's 2,700 kilometers downrange, which we actually heard it at. So we're communicating this object that's in space and actually seeing it. And this was definitely one of the highlights of my life right here, this picture. And so, which is kind of fun to share. And we also, after we launched it, we went, okay, we need to communicate with it. So we built a ground station in Lynn and Garrett's backyard. And so, which was interesting because I worked on the ground station later at Montana State University. It was the exact same component, so it really helped me with that. And just to kind of show the team, you have on the left-hand side Ben Cunningham, who actually went to Montana State University and was my roommate for 2 years. And he's still there finishing up his master's in electrical engineering. Then you have Garrett Jernigan and Hunter Mills, and of course our Steve Anderson right here, which and then me in the middle with longer hair. Still wear black. That hasn't changed. So, and then just to go into, to show you that I was actually here, and I did academic too. This is my actual transcript, which I was able to find when I was looking through all my graduate admissions stuff. And like I said, I wanted to kind of link not just the research, but the academic side to the graduate school. So I wanted to point out the classes that I know directly helped me. And how many of you are actually physics majors here? So there's 3 of you. So you guys are going to know a little bit more about this one. So 366 intermediate experiment I had with Dr. Shi. 460 quantum physics, 450 statistical physics with Dr. Jones, and then electricity and magnetism, analytical physics I had with Dr. Qualls, and the introduction to mathematical physics was probably my one that I used the most, and I didn't realize that that was going to be the one that I was going to use the most. And so that was something I really needed to pay attention to and work on.
Did you have that with Dr. Shi?
With Dr. Shi, yes. And then 381 was with Dr. Jones, and then I took an antenna theory class in the electrical engineering department with Dr. Khalil, which is a lot more physics-based than electrical engineering-based, at least the way he taught it, so because he actually went through with Maxwell's equations and derived a lot of things. So, so there you go. I actually went here, graduated, and then I applied to 10 different grad schools, and I got into 3. I got into Georgia Tech, University of in Logan, Utah, University of Utah, there we go, and Montana State University. And so when I went as a perspective to Montana State University to see what they had to offer, as a Californian, I'd seen the snow 3 times in my life. When I showed up there, it was minus 15 degrees Fahrenheit, and you could only see about 10 feet in front of you because of the snow. And I loved it. So I found out I loved the snow, and I walked in this every day about a mile to campus, and so in the snow, in this with just a normal jacket. So I don't know if I was crazy. But I started there with graduate physics, and I did 2 years of graduate physics. During that time, I was also a TA for Physics 262 and 263, which is an introduction to laboratory electronics for the physics majors there. So all of those students that I had were physics majors. And this was the first time that SSU basically helped me, because normally these classes are reserved for the upper echelon, upper graduate career people, because they were teaching physics people, not introductory physics to like engineers and artist majors and everything. And so because of the experiences that I had here, they were like, okay, you actually know a little bit about this. You can do the physics, you understand what a Bode plot is, so you get to teach this class. And so I got to have way easier grading, which is you'll find if you go to graduate school, grading is the bane of your existence because it takes forever. But they were all physics majors, and so they actually cared and they actually wanted to try, and it was really nice to have that. And then last year I switched and got my degree in electrical engineering because I wanted to do more hands-on things with my life with career-wise, and so I kind of chose that trajectory path. But the physics is the core background that I had, and it makes me a different engineer than most people because I can, when I'm talking to the scientists, especially on projects, I understand what they're talking about when they're talking about the science, about electron, oxygen, recombinations and lines and stuff like that. So the MSU campus, when I arrived there, this is not snowy, but the right-hand picture is a picture from the ground station up on the roof, and so I was working and I took a snapshot, and so you can kind of see the valley there. This is really close to Yellowstone and Glacier National Park, and if you've never been up there, go. It's absolutely gorgeous there. And then the left-hand side was part of my walk every day to the physics building. And so, like I said, the classes that tie in. So Physics 325 and Physics 381 helped me tremendously in my Physics 566 class, which was my Mathematical 1 physics class in graduate school. And so you can see that one of the projects we had to do a final project, was I did FT code and peak finding code written in C. So that's very much like the T-Logo cube. I took the idea and the methodology of how to do that, implemented it on an Arduino. And then the other thing that really helped, which was interesting, is during the last year here, we got a 3D printer. So I learned how to use 3D printing, and so to do a spinning test hardware setup, I actually 3D printed the entire jig and everything here so I could actually verify my code. And so, again, the things I learned at SSU were able to be helping me in various ways that I didn't even know were going to help me, because who would have thought that playing around with a 3D printer in the last year that I was here was going to make it so that I could quickly verify code for a math class in graduate physics. And it found the peak. So it worked, and I got an A. That was good. And then the next real one was Physics 430. So that's the E&M class. And so I have an example of my actual homework here and a little subset. And so the two classes that helped me with was Physics 425, which is E&M 2 undergraduate, and Physics 519, which is the graduate electromagnetic theory. And so one of the things I can say is that if you go to grad school and you come across something like E&M, don't be, if you're kind of shaky in it, don't worry about taking the undergraduate class. So like we don't have 2 E&M classes here, and so I took the second undergraduate E&M class at Montana State because it was able to help me move forward. And so don't be afraid of doing things like that, as long as, you know, talk to your department and talk to your advisor when you get there. But, you know, for me, when I came here, if you look at those transcripts, I took E&M my first semester I was here, so that would have been my junior year, and so I was probably taking that a little early, and so I was a little shaky on it, so I retook that. And so hopefully if you, have you guys done the E&M class here yet? So on the left-hand side, those of you can, does that kind of problem look familiar? A little bit. So that's pretty much straight out of Griffiths, and so don't get rid of your textbooks. That's the other thing. Don't get rid of your textbooks, because when you come across this, so we were doing Jackson E&M, which is a pretty typical physics textbook for E&M, and when you start reading it, it just jumps right in, and you go, okay, I don't even remember how to do a charge distribution on a sphere with an arbitrary charge potential in the middle, so let me go back to Griffiths, read about it, and then I was able to move forward. And so the other thing to kind of show on here, which is, this is kind of Physics 430 and 360, or the math class that we took here, I can't remember what it is now. A lot of math in the upper division physics here. Kind of the next main class was quantum, because there's 2 semesters of graduate quantum that I had to take. And so 460 really prepared me for that, because right off the bat, they're talking about raising and lowering operators. They don't gently bring you into the subject, and so you really need to have the foundation of your undergraduate classes. And so one of the things I highly recommend when you decide, if you decide to go to graduate school, especially in physics, is during that semester or summer between, just skim back over your books and just kind of get an idea of like, oh yeah, this is a raising lowering operator, or this is some other quantum well potential, because I did that, and that helped me, so that when these homework assignments started coming up, it's like, oh yeah, that's chapter 4 or 5, and I could go to that, and it would help me. And so again, you can kind of see on the left-hand side, for those of you who've taken quantum here, that looks like a pretty similar problem that you've probably done before, just finding an energy potential. It gets a lot more complicated as it goes on, but it's the beginning class, kind of stages of it. This was like homework 2 or something. And then going on to Physics 450, which is the thermodynamics stat math class that I had with Dr. Jones. And it was interesting because both his teaching style and also what he taught really prepared me for grad school, which was kind of interesting. And so he really makes you, at least, I don't know if he still does or anything, it'd be interesting if he was here, I could ask him, but he makes you work for it. And so he makes you think about what you're going to do, and he doesn't just necessarily go, here's your cookie cutter answer, you have to go and figure it out yourself, which is grad school. So that was one of the big things when you were coming across these kind of problems. And so I had the weird opportunity to take Physics 446, which is the undergraduate thermodynamic and stat math class. And so I was able to do an A/B comparison between our undergraduate stat math and their undergraduate stat math, because should be fairly similar. And I found that they were very similar. And so that's a good sign. Montana State University is a pretty good school, and they are a research school, and I was able to do both. And the reason why I took the class is they had a little bit more statistical mechanics, and I needed that for the qualifying exams in the physics, and so I decided to take it over again. And also the professor was really good, and so and I had a slot open in my needing units, so it's kind of filled in there. And then the actual StatMat class, 535, which was interesting. I'm just going to leave it at that. That was an interesting class. We ended up grading one of our own tests, so that was fun. All right, and then this is the last homework slide of my homework, I promise. Physics 320, which was probably, I keep saying this was the most useful class, but this again was one of the most useful classes because it directly related. Because we basically redid all of 320 in way more excruciating detail. And this class, even though it's classical mechanics, seems like it would be a lot easier than maybe like quantum or StatMac or any of those. This was the hardest class and the longest time-consuming class. Most of these homework assignments were like 30 to 40 pages long, and with multiple parts, and most of the time you couldn't finish it at all. And so you try to power through as much as you can. And again, going back to having as much resources as possible, having the undergraduate textbook, finding example problems that were similar and being able to actually use those materials, because you're trying to learn all this stuff, but you're also trying to get fast enough so that you can get to other things. And so you have to have a balance between actually finishing all your homework and learning it, and it's interesting. You have to find it for yourself. Everybody's slightly different. Some people are faster than others. Anyways, so this should also look very familiar with the Coriolis and centrifugal effect and everything, right? So going into graduate studies of what really you should do when you get there, and this could again be different for everybody else, and is you need to find a study space. So this image is what I stared at for a year. Right here, this was my cubicle that I had in our first year office. Eventually grew to 4 monitors, because I like monitors. And so you can recognize some of these books potentially. And, but the biggest thing is that you need to find a study space that is your own and that doesn't have any distractions. So at least at Montana State, they had a place called eWaste where you could get old computers. And so I had one of those computers. So I didn't have Facebook, I didn't have any games, I didn't have anything except for my schoolwork and any tools I needed for the schoolwork, like Mathematica, for example, which is another thing that 381 helped with. And so, and you'll find, I don't know, they could probably do a study that the people that didn't do this were a lot less successful. So if you had the distractions, people would use them. And so don't do that to yourself, because you're going to an hour 12 or 13 just want to take that 10-minute break to be able to watch that one YouTube video, and then 4 hours later you're like, okay, now all of a sudden, like, everybody's binge watched Netflix, I'm sure, and then it's been 4 o'clock in the morning going, yes, one more episode. So find a study space. The other thing is schedule your time. So to give a general idea, so the TA RA ships, so a TA is a teaching assistantship, RA is a research assistantship. RAs usually come second or third year, depending on what school you go to, and that's a minimum of like 20 hours a week. And this is amazing, this is great, because you get a stipend. So one of the things about graduate school, at least in the science fields, at least it seems, is that they pay for you to go to grad school. And if you don't get paid to go to grad school, go to a different school, or work a little harder on your GRE. So, because I got tuition waivers, healthcare for the first year, and I made about $2,200 a month. And so that was enough to be able to eat, pay rent, and do all that, especially in Montana. And it varied. If I went to Georgia Tech, I think it was closer to like $3,600 a month, which was kind of amazing. But they have a horrible housing shortage there, and so you're paying a lot more. So it kind of balances out. And then the other thing is to keep in mind, at least at Montana State, there's 3 graduate classes, and each of those have 10 to 20 hours of homework a week. Plus, you need to be studying for all your tests. Plus, if you're like I was, deficient on some of the math skills, you're having to be studying the math. So if you start adding these things up, you realize that it's way more than 40 hours a week. It's closer to 80 or 100 hours a week. And you then also have to study for your comprehensive exams, which is what allows you to get into either master's pass or PhD pass, and you have to do oral comps, and so you have to worry about all of that. And then the other biggest thing is the household task, which is everybody forgets about. So you got to go grocery shopping, because if you eat Jimmy John's every day, you'll go through your stipend way too fast, and 2, you'll gain 100 pounds because you haven't done that. And so grocery shopping takes an enormous amount of time, especially in the snow, depending on where you are, and then cleaning your house and doing other stuff like laundry. You'll find the graduate students that don't remember how to do this properly, and they kind of smell, and so don't be that person. The other thing is there's 2 types of graduate schools that I can ascertain, and maybe there's more, but there's ones that your fellow comrades are people in arms with you, and they help you and you help each other, and then there's other graduate schools where it seems like they're your enemy and they're competition. Me personally, I like the ones where they help each other, because I couldn't have gotten through grad school if I didn't have my other first years with me. And this is Mike Shumko. He's an awesome guy. He's doing graduate physics, and he's actually doing the data analysis on some of the satellites that I worked on, which is kind of interesting. So he's getting his PhD off some of my work that I did. And so he's doing some minimization there. And so work with others, and you need to share what you learned. Because if you kind of come across and you find something, don't hoard it, share it. And so you can see Dave's method here for some raising and lowering operators here. And so he figured out this, I think at 3 or 4 o'clock in the morning, wrote it on the board, and then when we all showed up the next morning, because he was kind of a late owl, we could see that and we'd go work it out our own. But the thing to keep in mind is that don't just take it and write it down, like all your classes. You have to rework it and understand what he did or what she did so that you can actually not be screwed on the test. And then the other thing is on the left-hand side, you can see that we're become kind of a group. So, he finished and he said, boom. It's like, the mic dropped because it was a really hard problem. I think we're working on this this particular problem for like 10 hours before we finally figured it out. And then you can see the news, it says, I love you guys, or something like that. Yeah, I love you all, there it is. So, we became a collective group, and even though I'm not there, I still get text messages from them at least once a week, and it's almost lifelong friends kind of thing that we figured out. So it's quite an experience on that. The other thing is to avoid distractions. So this is my umbrella cockatoo, which was making it so it was difficult to study. And so, again, like I said, don't be playing video games all the time. Right before you go to graduate school, don't do the Steam sale and download a bunch of games. Don't do that to yourself. Try to minimize what you have, because you really need to be focusing and paying attention. That being said, you also have to get out every once in a while. And the balance, again, the word balance comes in. You have to figure out how to do that appropriately, because if you do this every weekend, then you're not going to be able to succeed. But if you don't do it at all, then you're going to go through a mental breakdown, which definitely have seen that too. So anyways, those are kind of my hints at one way to do grad school. During that time, I worked at Space Science and Engineering Laboratory, SSCL, as a graduate student, and then as a full-time research engineer while I was finishing up my master's. And I worked on 3 main projects and a bunch of other ones, but additive manufacturing, GPS antenna, and then 2 satellites that were 3Us. And then I also managed the undergraduate students and was a lab manager. And one of the things that really helped me with that was the SPS work that I did. So I was one of the outreach officer, I don't know if that position's still there, and doing some of the tutorial work, because it allowed me to figure out how to interact with people appropriately. So interacting with the other graduate students or undergrads was a skill that I needed. And also the brain scratch on that. TA work really went hand in hand with all of the tutoring work. So the additive manufacturing GPS antenna is directly related to ES384, the antenna theory. So it's literally the exact same program that we used, CST Microwave Studio. And so built this L1 band right-hand circular polarized antenna. And this was for a company called Draper, which does DoD work. And it was basically trying to figure out how to put antennas into 3D printed drones. And so that they could be somewhere off in Afghanistan or whatever in 3D printed drone and have all of the work and then have it go. It was kind of interesting. Didn't get that far. We just kind of did the test samples to see whether this was actually practical to put radiating elements inside for 3D printed material. But again, I was working with 3D printed material. And I was working with University of Texas, El Paso, which is one other thing that's really cool about being in grad school is you get to go places. So I went to Texas, had amazing Mexican food, and was able to see their facility. And they did amazing work with 3D printing hip bones, and you see all kinds of things that are kind of cool. And then again, when it came back, verified everything with the vector network analyzer. And so I learned all of this stuff at SSU. This entire thing could have just been given to one of the students here, and they could have done this work. And I was able to do it as a grad student. Now the satellites, there's 2 of them. The first one is RadSat-G, which is partly a undergraduate, partly a graduate satellite that kind of melded into one. There's 2 separate and then moved together. And this was testing a radiation tolerant computer stack using an FPGA. And that was the science payload side. And I did the avionics side. So the avionics stack, this was kind of my domain here. And Ben Cunningham, one of the guys that worked with me on T-Logo Cube, was on this project at Montana State. And so he built one of these boards, the MFIB, the multi-function interface board, and I built the power system board, and then we used commercial off-the-shelf or COTS for the CNDH, the command and data handling. And this whole thing was drafted by an undergrad, one of the undergrad mechies, mechanical engineers. And so you work closely with your undergraduate people on your team. So usually when you're building a satellite or you're building anything, you have 3 or 4 graduate students and then an army of undergrads. And so learning how to use your resources wisely and keep in mind that they also have homework and schedules and things are important. And so on here, some of the antenna theory came in of designing where the solar panels go for the radiating element needs to be in the center of the spacecraft for the antenna, and some of the weight distribution. And the biggest thing that using the physics here, which was some of the analytical mechanics style, is that the magnetic board. And so satellites, this satellite was passively magnetically stable, and so it has a dipole antenna or dipole magnet in it with some hysteresis rods, and it basically follows the magnetic field lines as it goes through the Earth magnetic field, and so it ends up flipping over every once in orbit. And so there's programs for this, and so having the physics background, I was able to understand what calculations they were actually doing, and then was able to find some issues with their program and size the magnet appropriately. So again, physics to the rescue on this. And so I built the EPS system, the electrical power system. So you can see that the sophistication from T-Logo Cube got a little bit larger because a little bit more time and understanding, but it was the foundation and basis. So if you actually look at the way I laid out the traces in the boards and you looked at T-Logo Cube, they're very similar, which is kind of interesting. So I went to a 4-layer board, and I actually got my thesis off that, which is an electrical power system implementing fixed power point tracking with temperature compensation. So it's a mouthful, but basically there's 2 types of power point tracking. There's maximum power point tracking and fixed power point tracking, which I discovered. So maximum power point tracking uses a hunt and seek algorithm to try to find where in the curve, the IV curve, the maximum power extraction can be. But on a satellite that's spinning fairly quickly, it spends too much time off the maximum power point and it doesn't work very well. You have to have different algorithms that aren't really available to civilians, maybe. And so realizing that the solar cells are bought prior to it, we have a priori information of what that maximum power point curve should be, and so we can actually just set the voltage set point and then use temperature compensation because that's the first order change from the power point. Anyways, not to bore you too much with those details. And then also designed the radio board, which is again same amateur band, 70 centimeter amateur band that we flew T-Logo Cube in. And then managed the undergrad students, and so again, got to travel. So this is Romy and Kieran. So Romy was an industrial engineer. She did all of our scheduling, which was really nice to have that. And then Kieran was our lead mechanical engineer, and so the next model you'll see of It Spins, he actually designed that. And he ran himself, then undergrads underneath him. And so we kind of had a hierarchy structure, which was kind of interesting. But we were able to go to Logan, Utah to do a small sat convention that was about a week long. And so we took 7 or 8 undergrads from our SSEL, and I got to go as well. So you do traveling. Now the thing that's nice about that is you got to travel, but then you also have to balance that with the 100 hours of homework and everything you have to do. So it's kind of interesting. It's a double-edged sword of, yeah, I got to travel, and then now how do I make up all those hours that I was gone? So be aware of that, and don't necessarily sign up for too many things on going. So It Spins is probably the coolest physics experiment side of that I did. And this is a satellite that basically, it rotates at 2 RPM lengthwise, so in the plane of the orbit, and it has a single pixel scanning photometer, and it does 6-degree integrations of field of view, and it has a strontium fluoride filter that's heated to 100 degrees Celsius. So it has a very, very narrow bandpass filter looking at oxygen electron recombination lines of electrons in the upper ionosphere. And so what that does is if you're taking these slices and points of movement and you know where you are in the orbit, you can do something called reverse tomographic inversion, just like an MRI does, and you get electron densities in the ionosphere with a satellite that cost, this was I think a $1.5 million mission or something like that, that was way over bloated for the instrumentation, but we actually built the thing for less than 200K, which is astonishing for what it is. And we also had a ADCS, which is attitude, determination, and control. And so my physics background allowed me to understand what the scientists were talking about for their requirements of pointing knowledge and also being able to talk to the ADCS people and understand what they're talking about when they're Earth horizon sensors, and how potentially you could have basically a thermometer looking as this thing's spinning, and it goes from the cold space to Earth, and how you can have the inflection points, and then if you have 8 of those sensors, how you could mathematically make a model to figure out which plane of the orbit you're in. And so it's kind of interesting. We did some MATLAB simulations, so using heavily on the physics, helping with one of the undergraduate physics students. He did a lot of that math to figure out how to put in those parameters so we can kind of understand how this satellite was supposed to work and spin. And again, I worked on the power system. It's kind of what my specialty turned into. This is a much more complicated board, whereas a 6-layer board did a little bit of noise mitigation with separating the digital log and analog circuitry, and then got to design some coarse sun sensor circuitry for the ADCS. So this is all kind of spun out of the knowledge from T-Logo Cube, which is kind of neat to think about. So, yeah.
The antenna on the IT students wraps around the middle?
Yeah, it's pointing out the side, so it
Single?
spins. Yeah, it's a monopole.
Uh-huh.
Yeah, so it just makes it easier to do the calculations, and the link budgets work out with them. And so there's actually 2 twin satellites on orbit called the Firebird missions that are looking at electron microbursts. And so SSEL basically dealt with the Sun-Earth interaction with the magnetic field. And so they're looking at electron microbursts for basically how charge is dumped from the Van Allen belts down. And so there's twin satellites doing spatial and temporal resolution of these things. So they're flying in tandem and they're slowly separated, which is kind of cool. And they flew those antenna types and it worked. And they're on their 3rd anniversary of working. And there's 2 people getting PhDs off that and working with other scientists and NASA scientists and stuff. So kind of the next thing I learned, this was helped me with the physics of semiconductors class that I took to understand the IV curve idea, which also helped me on my thesis. We ran some voltage set point IV curve measurement for our partner Solero. So as an undergraduate university, you don't have enough money for any of your projects. And so if you team up with industrial partners and do something for them. So what we did is we teamed up with Solero. They gave us free solar cells, and we ran IV curves of their cells in orbit so that they have higher test readiness levels. Well, when they sell to NASA, they can go, here, this is worth your millions of dollars because it's already been flown on orbit, and here's your characteristics. And so what was fun is actually designing the voltage set point IV curves, because most of the IV curves are current set points, if any of that makes any sense to people. And so hopefully I'll be finishing writing a paper on how to do this method. And that's mainly for, I believe, so that they can do a comparison through radiation degradation over time on orbit, because the current set points, it's kind of fuzzy how to do that. So I got to work with their scientists on figuring out how to do this. Did some more Arduino work. So this EGSE, electrical ground support equipment, is very similar to the S4 program. So it does an Arduino, used the same kind of control interface software that I used on S4. So again, more work from SSU that kind of directly translates those building off of that. And then L3 in control, doing some graphical user interface. And so Physics 381, of course, directly related here because you learn a little bit about C, and there's some background and analysis stuff with MATLAB that we learned how to do in that class. And then can recognize this ground station, looks very familiar because it looks like the one that was in the backyard of Garrett's house, Lynn Garrett's house. It was the exact same ground station, pretty much, the same components, the same everything. And so I got to be the guy that worked on it, which was fun. And so I'm like a 8-story building and then up further. And so got to see a gorgeous view. And so I got to be the guy that went up there and fixed everything. So that was a lot of fun.
Kevin, how high were you on that? I mean, you're saying you're an 8-story building, but how far up is the tower? I mean, do you have a feeling you're a fair ways off the ground of the building?
It's like I think like a 20-foot tower on the top. So it was like probably total like 10 stories high where I was. It was, I think, the tallest point in Bozeman, actually. So that was a lot of fun.
Is that a selfie?
Yes, yes. I don't normally take selfies, but that was a selfie.
Well, after that one.
There's also a lot of other like pictures of the thing that was broken that I fixed. So, and then I did also all the assembly integration and testing, which Physics 366 really helped me with. So one of the biggest things as a graduate student going into a place, or if you're doing research here, that I found is that when you walk up to a machine that's $500,000, it's kind of nerve-wracking to use it. And so one of the things that 366 did, because we used the SEM, the scanning electron microscope here, and the thermal deprivation, wow, I can't speak. Yes.
Deposition.
Thank you, deposition chamber. Got used to walking up to equipment that I didn't know how to use and just kind of start playing with it because I realized that I'm most likely not going to break it as long as I'm safe about what I'm doing. And so we did a lot of vacuum testing, so we had our own bell jar that we were able to get down to 10 to the minus 7 torr pretty easily and do thermal bakeouts for these things. As well as I was working in a flow bench with all the ESD precautions, so that is a black ESD jacket. And then my partner there also wore one. And so, and then you do a lot of documentation and verification testing when you're doing research, and so get used to writing documents that are very elaborate. And then I'm just going to show you a quick video of a really cool build-up. And this is the other kind of lab. So this is one of the labs that we worked in. So it's a little bit bigger, which was nice. You could walk around, and you didn't have to bump into each other. You actually had stations. So that was my office mate and partner there, Matt Hanley, who's now at Los Alamos National Laboratory doing very similar work for a ridiculous amount of money. So this is It Spins. So the left-hand side is Matt Hanley, and then I'm up on the right-hand side. And so this is the Avionics stack that we're putting together. And I had made all of those harnesses already, working with my mechanical engineer to get lengths. And you have to make everything ourselves. Are we running out of time?
There you go.
Oh, just kidding. Okay. You have to make everything ourselves because you have to worry about outgassing. And so you have to, all your materials that you put in a spacecraft, you have to make sure that meets the NASA outgassing standards or else they won't launch you. And so we had to use a wire called PTFE as the installation type. And so you can't buy stuff that off the shelf. And so you had to make everything. And so I got to do a little bit of harnessing work, but working with my mechanical engineer to figure out the lengths that I needed to cut these things at. And then building up the battery pack there. And so these are 5-second times between the things. So this is about a 4-hour build up in 2 minutes. And you can't see, but we're actually going off an entire document that my mechanical engineering team put together. It was, I think, almost 100 pages with actually drawings of each screw that needs to go in what place and what torque and everything that my undergraduate team put together that we're checking off and making sure we're doing. And they're actually in the background, and you'll see them in just a second. So that's the instrument that's going in. That's C-tip. That's the single pixel photometer. And then we're measuring some things to make sure it's not going to mess up. And then putting blank solar panels on, because you don't want to handle things, solar cells, which is kind of interesting going back, seeing some of the pictures of T-Logo days and going, oh my God, I can't believe we're touching that with bare hands. And so these are my undergraduates here. So Tom and Kieran, and they just tied up the antenna so that we can do an antenna burn launch, or antenna fire, because it's deployed. Basically, it's a monofilament or a fishing line through a coil of nichrome wire that gets heated up, melts the wire, and deploys the antenna after launch. And there we are, stripping everything down because we realized that we may have had a problem, and so we're kind of like trying to take it apart as fast as we can. We didn't have a problem. It was good. So speaking of touching things that are expensive, so I worked also on a sounding rocket. This was entirely in the physics department, so there was no electrical engineers here. And so all of everything was built by physicists, and we were partnered with Marshall Space Flight Center, and they built the ESIS camera system. MOSIS was the third reflight, so these sounding rockets go up to 260 kilometers. They're up in for about 10 minutes, and so basically what this rocket did was it shot straight up, got in space, turned around, looked at the sun, and it had their camera system split it into 3 channels so they could look at Doppler shift, and so they could actually look at a sunspot and then see the material, whether it's falling or going into the sun and at what speed. And so they're actually able to do that, plus with the all the other observations, see what kind of clarity of the sunspots were, and so they're doing a lot of research on that. These cameras right here, the ESIS side, which were designed by Marshall, and they all went on a conference, and so I was the only person there. And so I got to work with the Marshall engineers to put this in. These are $500,000 cameras, And as he's just going, oh yeah, take that apart and do this, I'm like handling these things, like $500,000 worth of stuff in a clean room, which was quite exciting and also very nerve-wracking. So when I got done, my heart was pounding pretty good, and but it worked. Everything worked, and did all the harnessing work for the electronics. So repackaged it, and again, a lot of documentation and cross verification. Spent a lot of time documenting things because basically the motto is if it wasn't documented, it didn't happen. So basically, that's the summary of some of the research that I did. There was other projects that I did, which was fun to try to integrate with classwork. But basically, the bottom takeaway is that I think it's worth it, but you need to put in the time. And my class, there was a 75% retention rate, which was really high, because normally it's around 50 or 60 are the percent of the people that actually graduate. And if you look at every one of those that didn't make it, they're the ones that had games on the computer. They're the ones that weren't in there on the weekend because they were off doing whatever, and they weren't there working with you. And so if you want to do that, you got to put in the time and realize that your next 2 years, that's it. That's what you're doing. You're not doing anything else. And so if you want to make that commitment, you can do it. It's going to be hard, but I think it's worth it. Other people might not think it's worth it, but I think it's worth it. So with that, do you have any other questions about grad school?
Did this one make it?
Yes, yes. She's 9 years old right now, and she'll outlive me. They live 80 plus years, so yeah.
I just have kind of an initial one, going through the entirety of this. I wanted to ask kind of what's the dynamic between engineers and the physicists and scientists working on the project, and how effective would you say communication is? You kind of seem to be in a pretty niche position, having the science background and the engineering. So do they talk well to each other, or is there a fundamental disconnect?
It depends on what project. I know that with like, what?
Can you repeat the question
Oh.
as best you understood it?
Okay, basically how the interaction between engineers, physicists, and scientists work on these kind of projects, and if they work well together or if there's communication issues. Basically, it's project dependent. There's a couple of projects that Matt Hanley and I ran. We used a software suite to kind of help communication facilitation between all of our different undergrads, and we were able to kind of tease out the problems using that. Other ones like the rocket project, that had a big disconnect between any of the consultants, the mechanical engineers and the physicists, because they just didn't know how to speak the same language. Was what I was kind of finding with that. SCCL was kind of built on a collaboration between physicists and engineers, and it's under the physics department. So even though that majority of the people working there were engineers, it was in the physics department, and so they kind of had to learn the physics language a little bit more, I would have to say, if they wanted to be there. And usually the way that kind of went is that people would start in their freshman year, they'd kind of observe, they'd learn the language because there's a ridiculous amount of acronyms. That's the other thing, is that when you first start in these things, you have no idea what they're saying because there's way too many acronyms. And so, so yes and no. It was good and bad depending on the project.
So you mentioned a lot of upper division classes, and I think one of the things that a lot of students are interested about, especially when they're starting out, be it in high school or early on in university, is when you encounter the introductory physics classes. And so we saw a transition between the upper division physics here at SSU to the sort of symbolic nightmare you showed us on the whiteboard. Did you ever struggle in your early physics career when you were adjusting to it for the first time, or were you just great at it from the beginning and I've destroyed my own point?
No, so you're talking about for me personally.
Yeah, so I think because a lot of us who are in the physics department can see that transition into grad school. I'm just thinking sort of if you could comment about the earlier transition into the very early part of physics, which seems so simplistic by these standards, but often challenging at the time.
Yeah, it was interesting because I came from the JC, so I didn't do the undergrad, like the lower division undergrad physics here. So not only did I transition like from there, but schools. And so there is a difference. The JC seemed to do pretty well at using symbolic, and I know that the professors over there really kind of push their students, because I know that coming here, it didn't seem like that much of a challenge for the JC transfer students because of what kind of classes they push there. So Sorry if I'm
No.
pushing
So
over.
I was saying, so a lot of people start off and to physics, many people like just F equals ma,
Yes.
right, and things like this. And was all that just easy to you when you first encountered it? When you first started progressing in physics, what was that like?
Oh, yeah, no, so progressing in physics from the beginning, no, that was not easy for me, because I was, you know, an electrician. I worked with my hands, I didn't use my brain that much, and then all of a sudden getting thrust into school where all of a sudden I had to learn how to use calculus. And so I was taking calculus and taking physics at the same time, and I probably spent close to what I'd spent in grad school at the very beginning to just get caught up, because I went back to school as somebody that didn't do too well in school, especially in the very beginning. Like, I did not do well in high school and everything, and so I had to retake a lot of classes. And so that was very difficult for me personally, and so yes, I spent a lot of time on that. One thing I can comment on is doing the TA work. We did learning centers basically, and you can see the difference between the lower division, upper division, and the main difference was trying to teach them to not just put numbers in their calculator. I think that was the biggest thing, because they didn't want to solve it symbolically, right? And then we tried to force them to every time that they would come in, because you'd actually find the problem, and then usually they learned it better. But
Other questions?
In one of your slides, you showed a physics class that was more mathematical based. Just out of curiosity, what type of math did you end up using in there? Was it just calculus or?
no. Okay, so what kind of math was I using in my mathematical graduate physics classes?
Yeah.
Everything. So one of the things I didn't say, which was interesting, we used the same textbook as the physics here. We used the Riley book. I think you guys are still using that. The big book, just a ridiculous amount of stuff. We didn't do homework out of that, but we used that as kind of our test thing. No, we did some calculus. So you started off with like ODEs, PDEs. We did differential equations. So we're solving like the broomstick on a finger and trying to stabilize it. So that was one of our homework questions. And then we went into like imaginary, what is it called? Imaginary calculus, where you have branch cuts and stuff. Complex cut, yeah. So we did that kind of for a while. And so basically the first class of that series was very similar to 325. The second series was more computer based. That was more like 381. And so we learned how to program to solve ODEs. We did run cut method. We did other kind of solving heat maps and different hysteresis grant things and Fourier transforms and filters and all on the computer side of things. And so it's kind of an interesting.
Cool. Thank you.
Just to follow up to his question, with regard like ODEs, did you ever design any programs that will help you go through and fix that mathematics or deal with it for you, just kind of creating specialized programs at all?
I didn't. So I took a little bit different trajectory because I was I did applied physics. My friends, they were doing gravity wave stuff, and so they built their own ODE solvers. They built all of their own programs, and they do ridiculous math that I don't even understand what they were doing, because they would talk to me about, like, I'd look at their programs and help them debug only on a syntactic or symbolic level. I didn't know what they were doing. They were doing like Bayesian wave theory and things. So if you want to take the theoretical route, there's a lot more of that kind of math and developing your own kind of solving programs. Yeah.
Do you want to comment about the physics GRE?
Sure. Might not be a popular opinion, but I think the GRE is, can you do bad physics fast? So I was probably, in my class, I was towards the bottom. I struggle a lot because of various reasons in my background and everything. And I had the highest GRE score.
Wow.
And so, Phil and Dave, they all were about 10 or 15 points below me. And we came to a thing mathematically, and they're like, oh, that's just like a Legendre expansion of, here's the gammas, this is what this is equal to. And it's like, I don't even know what you're talking about. So, yeah, the physics GRE, it's a necessary tool to get into grad school. You need to really study it. You need to figure out how to do the unit analysis so that you can do bad physics fast, is what I'm calling it. And once you get done with that, that's all well and good. It's not indicative of whether or not you're going to be good in grad school, I don't think. What's really is your motivation and what kind of work you're willing to put into it. So that's my opinion of the GRE. And honestly, I think the best thing to do the GRE is if it was a mathematical GRE, because the math was, at least for me, was the weakest subject. And so if I could have taken like the PDE class here, I would have. So I would have taken as many math classes as I possibly could if I was going to go into graduate physics. Any other questions?
Just going back to your undergraduate, the T logo cube.
Yeah.
When I was reading your display of like the research you did and everything, it was talking about how it was used to find data on like X-ray, I believe. Correct me if I'm wrong. This is just from like remembering. And I wanted to know, like, from knowing that data, like, what does that say? Like, why is it important for you or for like people to even just make these, to make this, to then collect this data? Like, what is the significance of it?
Okay, so basically the question was integrating the CGT array, I believe, to do the X-ray detection on T-Logo Cube. That instrumentation didn't actually fly on T-Logo Cube because we didn't have enough time to actually test it, since normally these development cycles are a year or two, like at minimum, and we only had 3 months. And so we had all the circuitry laid out, ready to go for doing the detection of the hard X-rays. That particular launch would have been probably raising the TRL level in testing and making sure that it worked well on orbit. But you can do a ridiculous amount of things with a hard X-ray detector. You could ask Garrett Jernigan probably way more about that, and he'd probably love to talk to you about that kind of science. But sorry.
I think something that resonated for me that you made was the idea of motivating work and finding time for things. And especially with a lot of undergraduate students, we see elements of learning to work not purely motivated by a deadline, but to put in extra work around that structure. Where in your sort of starting off did you sort of really feel you made that transition from a sort of passive to completely active?
To putting in the work to be able to,
Really
that
good.
was from the very beginning. At grad school. Like I showed up early, and then I started rereading. I reread the quantum book. I reread the E&M book. I started preparing for these classes before I took them because I looked at what the homework looked like because it was up on the internet, and I went, okay, these are the classes I'm going to take, and I saw it, and I have no idea what's going on here. And so basically, I went into panic mode and went, okay, I really need to. If I'm going to do this, I need to really just be able to hit the ground running. And so, and if you go to grad school, you're going to have to do that. You're going to have to hit the ground running. You can't, if you lose a week or two because you're slow and not realizing that, like, oh, I need to actually be putting in the 20 hours on the first homework assignment so that you can have a foundation and just even work ethic, it's not going to go well. So, right away. Any other questions?
What's a level 2 Rocketeer?
Level 2
How
Rocketeer.
many levels are there?
There's 3. Yes, there's 3. So basically, you can go to the not the grocery store, but like a store, and you can get the little Estes rocket engines, and you only get to go up to a certain engine size, and then you can get your level 1, and then I think you can do like J and K or something like that, or I can't remember anymore. It's been way too long. Maybe Lynn remembers.
Level 1 gets you H and I.
H and I.
And level 2 gets you to J and K.
Okay.
Every letter is a factor of 2 more for us.
Yeah.
So model rockets are A through P.
Yeah. So to give you an
Level
idea.
2, you have to pass the safety test also.
Yeah.
Level 3 is like half.
Level 3, you have to actually design your own little payload with 2 different ways of blowing with parachute. None of us ever made it to level 3. But Kevin and me and Logan all got to level 2, and that was good enough for what we were doing.
Teacher training, because these rockets are 6 feet tall, go around, and so we got up to like 3,600 feet, and then your little rocket I think got up to 50,000.
My rocket went to 10. My level 2 rocket went to 10,000.
10,000. Okay.
Your level 2 rocket went to 6,000 feet.
Okay.
This was bigger and heavier. Mine was a minimum diameter one, but I was trying to see how high I could get.
Yeah, and when we actually went out to the Black Rock Desert, they won the Carmack Rose. They went to
Yeah, they went to 109,000
feet.
Yeah, and then they won the prize for the first GPS verified amateur rocket over 100K.
Yeah, all with stuff you can buy. So.
But those are a bunch of level 3 guys that did that.
Yeah, was a lot of fun. Unless you have a really good job, I don't think you could afford it because it's one of those things. Those motors are like $100 or more, and they burn out in 0.3 seconds. So if you think about the entertainment per cost dollar value, that's just ridiculous amount of money. You know, you could. So. Any other?
Scales, actually.
What?
It probably scales.
Yeah.
All right, well, our speaker will be staying with us for dinner, so let me know if you'd like to come and join us this evening for dinner with the speaker. Elsewise, let's show our appreciation and thank you.